Alright, so today what we're going to talk about is exponential decay. So exponential growth is what we originally started off working. It was basically, what if I had one bacteria and it splits into two, and then you have two bacteria, and then those two split, and then you get four, and those four split, and then you get 8, and then those 8 split, and you get 16. Now, this would be the opposite. We're going to work on the decay. So it's going to be backwards, going backwards, as in, like, what if I had 1,000 bacteria and I was, killing them like an antibiotic? Like, how many would be left at a certain amount of time? So if I put antibiotics into 1,000 bacteria, this 1,000 bacteria per hour, say, it would decrease by half every time. It would go from 1,000 to 500 to 250 to 125, and then on into halves. So that's a decay, is when it's decreasing instead of increasing. Now, what makes the difference between a growth and a decay would just be the b value, or what it's multiplying by every time. If it's b is greater than 1, it's growth. B is less than 1, it's decay. So with that, let me give you guys your Chan Academy problems. So the first one is 64 parentheses 1/2 to the power of x. Now, this time I didn't make you guys do all the negatives, but it's good practice if you do more negatives. But I just want you guys to do -1 all the way to 3 for this table. You don't have to graph it, just table it. You're okay to use a calculator, I guess. And 10,000, and then parentheses 0.1. Remember, this is the same thing as 1/10 to the power of x. Do it from -1 to 3, and then table it. So you don't need to actually do the -2 or -3, but if you want to, that'd be good practice. You can use a calculator if you want. Okay. Alright, so now I'm going to go into how to solve these. Alright, so exponential decay is nothing different. You already have this form, y equals a parentheses b to the power of x, and sometimes we'll have the plus d here and the plus c down here. And the only reason why we did that is we wanted you to see the transformations of, if I had y equals 2 to the x and y equals 2 to the power of x plus 1, what does that do? Oh, it just takes everything and moves it up 1. So everything's essentially like a transformation. Okay, but sometimes it's just easier to do the transformation, or to just do the table and then graph it. So exponential decay, b needs to be less than 1. Okay, and if it's growth, b has to be greater than 1. Okay, so suppose I give you an equation, y is equal to, let's do 1,000 times 0.1 to the power of x. Okay, and I'm telling you to table it for x, y, and then graph it, which we'll do on Desmos. Alright, so for this one, the first thing I would do is change this 0.1 and think of it the same way as 1/10, right? Decimals, it's the same thing as 1/10 in a fraction. So I'm going to go ahead and do something like 0. Alright, so 1,000 parentheses 1/10 to the power of 0. So I'll write that in red. It would be 1,000 1/10 to the power of 0. When I plug in x as 0, I'll get that. So 1/10 to the power of 0, that gives me 1. 1 times 1,000 gives me 1,000. Alright, now the next one I'll do is 1. Now that would be 1,000 times 1/10 to the power of 1, and that's just 1,000 times 1/10, and that would give me 100. And if I follow the pattern here, I know the b is 1/10, so oops, sorry. I know it's going to be 100. I know it's multiplying by 1/10, so I know the next one's going to be 10, and the third one's just going to be 1. Now going back the other way, you can kind of guess what -1 is going to be. Well, to do it mathematically, I'll do it first. It would be y is equal to 1,000 times 1/10 to the -1. Now any fraction to a negative, or anything to a negative power, is going to flip. So this would be the same thing as 1,000 times 10 over 1 to the power of 1. And that's the same thing as just, 10 over 1 to the power 1. That's the same thing as 10. So it'd be 1,000 times 10. Alright, now you multiply those together and you get one extra 0, so it'd be 10,000. So from 1,000 it becomes 10,000. Right? And obviously negative 2, if we just kept going back, it would be 100,000. And you guessed it, if I did negative 3, it would be 1 million. Okay. Alright, and this is basically decay. So let's go ahead and try plotting this in Desmos. And I had points like 0 and 1,000. I'm going to zoom this out so you can see it better. 0 and 1,000. 1 and 100. 2 and 10. 3 and 1. And I have to go the other way. 1 and 10,000. Oops. It would be negative 1,000. Oh man. Alright. And then it would be negative 2 and 100,000. And this actually doesn't look out as great as I want it to be. So let me just put in the function. It's going to be y is equal to 1,000, parentheses 0.1 to the power of x. And even though it looks pretty weird here, it looks like a straight L, what you're supposed to see is a curviness to it. So at 3 you got 1, at 2 you got 10, at 1 you should be at 100, and then going out you realize that it's really hard to graph. Okay, so it's going down and then it slows down, and it's basically the opposite of a growth. And again, our range for this one, you'll realize it's the same. It's 0 to infinity, because it never actually touches 0. Okay. And the thing about exponentials and graphing it when they're large numbers, like the example I'm giving you, it's going to be difficult. You basically just want to get this part where it slows down and the part where it explodes up. Okay. Whereas, zooming out, it's going to be pretty difficult to see. Okay. So as far as decay goes, there's not too much of a difference. If you can plot the points, you're good. Plot the points, and then you should know that it's going to be looking down like this way. Okay, this is decay. Whereas for growth, it's going to be the other way. Growth. Nothing's really changed as far as the word problems. This is your initial amount. And this would be your ratio. Okay. In this case, our ratio was 1/10. Because you see every time that you're multiplying by 1/10. 1/10. Every time multiplied. Alright, so I know that it's kind of longer video, but I just kind of took my time and worked everything out. I feel like decay should be okay. If you guys get growth, just the graph will look different. It'll look more like this one, the decay look. Okay. And we'll go work into word problems and stuff like that a little later, like as in the next lesson. But other than that, for this unit, there's not a lot left. We've done growth, then we did geometric, and in geometric we did both geometric sequences that grow and geometric sequences that decay, because we did one on the quiz where it's like 500, then 250, 125, on, and that was with a ratio of half. So that was essentially like a decay, but it wasn't a function, it was a sequence. So this is the last topic pretty much, and if you guys are lost or anything like that, just come see me or send me an email. It's achan@fc.spusd.net. Okay. There's a homework check for this one, so make sure you have it, remind your friends. Alright, thanks.